Throughout the centuries, people have experimented with different substances to create desired reactions. Here, a hole is being drilled in the ground in which an explosive will be placed so that underlying rock can be loosened and mined. The charge is a mix of different chemicals that is put to use in this quarry to cause the explosion. During the next few minutes, we are going to take a look at different types of matter, such as elements and compounds. We will also explore the basic structure of the atom. Do you have any idea what these three substances have in common? Ice, the solid form of water, helium gas, filling this balloon, and dry ice made of carbon dioxide. They are all pure substances. A pure substance is made up of one kind of material which has definite properties. It is the same throughout. Let us take salt, for example. Salt is a pure substance that has a definite square-shaped crystal. Salt has a white color and it has a salty taste. These are just a few of its properties. Many pure substances are made up of simple pure substances called elements. Aluminum is an element in this can. An element is a simple pure substance. An element cannot be changed into a simpler substance. There are over 100 known elements that make up the matter in our surroundings, and all matter is made of elements. This jewelry contains the element silver, a shiny metal used in making jewelry. And this screw is made up mostly of the element iron, a metal that rusts over time. We know that all objects are made of matter, and that matter has mass and volume. This liquid is mercury. As you can see, it can be divided into smaller and smaller drops. Do you think it is possible to create the smallest piece of mercury that cannot be divided any further? Or what do you think the smallest piece of matter these rocks can be crushed into? It is impossible with the naked eye to see the smallest particle of matter. But through the ages, people have attempted to find the building blocks of matter in direct evidence. For example, how do we know the wind exists? We cannot see the wind, but we can see the effect of wind moving objects. And we can hear wind whistling through the trees. And we can feel wind. Scientists have had to make similar indirect observations about building blocks of matter since the time of the ancient Greeks, who concluded that matter could not be divided into smaller pieces forever. The smallest possible piece of matter could be obtained. They used the Greek word atomos, which means not to cut or indivisible, to describe the smallest piece of matter. Today, we call it the atom. This rock contains an element called copper. Copper is commonly used in pipes that carry water and in wires that carry electricity. What do you think we would end up with if we cut up this piece of copper to its smallest piece? With the assistance of very specialized equipment, eventually you would end up with the smallest piece of the element copper, called an atom. This is a diagram of an atom magnified many times. An atom is the smallest piece of matter that cannot be commonly broken down. Atoms of the same element are alike. For example, this chain contains gold atoms. Nearly 2,000 years after the ancient Greeks made their initial theories of the atom, an English chemist by the name of John Dalton conducted an experiment in the early 1800s, leading to the widespread acceptance of the idea of the existence of atoms. Conducting experiments with gases, decided that elements have particles that combine in simple ways. He pictured particles as simple spheres. Dalton's theories had the following parts. First, all matter is made of atoms that can be combined. Second, atoms of the same element are exactly alike. Third, atoms of different elements are different. And fourth, atoms of two or more elements can be combined to form new substances. Dalton made tremendous contributions to the understanding of the atom, but his discoveries were not complete. Toward the end of the 19th century, J.J. Thomson, an English scientist, found that atoms were not simple, solid spheres. He discovered a very important component of the atom that we put to use every day in the form of electricity and in magnets. He discovered electrons. Electrons are small particles located outside the nucleus that have a negative charge and cause the magnetic needle in the compass to point north. In 1911, Ernest Rutherford added more to our understanding of the atom. He fired a stream of positively charged particles at a thin sheet of gold foil. He found that most particles passed right through the gold atoms in the sheet of foil. He concluded the atoms were mostly made of space. Some particles, however, were deflected by the gold foil. He concluded that the atom had a small, dense, positively charged center that repelled the positively charged bullets. He called the center of the atom the nucleus. The nucleus is very tiny compared to the atom as a whole, equivalent in ratio to a marble in a stadium. Rutherford stated that all an atom's positively charged particles were in the nucleus, and negatively charged particles were scattered outside the nucleus around the perimeter of the atom. A couple of years after Rutherford's contributions to the understanding of the atom, Niels Bohr proposed that electrons orbit around the nucleus. He stated that each electron has a fixed amount of energy, and that the electrons orbit within energy levels, forming rings around the nucleus, similar to the layers of skin around an onion. The energy levels in Bohr's model can be compared to a ladder with rungs. As you climb the rungs of the ladder away from the nucleus, the amount of energy increases. By absorbing or releasing energy, an electron can move between energy levels, similar to climbing up or down a ladder. While today scientists agree that electrons orbit the nucleus in energy levels, they do not do so in regular paths. Instead, electrons dart in ever-changing paths within energy levels. They form what is referred to as an electron cloud. The electron cloud represents the region where electrons would probably be found swirling around the nucleus of an atom. The bright flame in this flare is generated by a combination of elements. The active ingredients are a blend of more than one element. A compound is a pure substance that is made of more than one element. Nearly everything you come in contact with is made of different combinations of elements, or compounds. There are millions of compounds. While some compounds, such as water, are made of hydrogen and oxygen, others are quite complex, such as plastics, made of dozens of compounds. Compounds are made of molecules. If we were to break down this piece of salt into the smallest piece of matter that still had the properties of salt, we would have a molecule. A molecule is two or more atoms with specific properties that are bonded together. It is the smallest piece of a compound that still has the properties of a compound. These are salt molecules, with a large atom of chlorine and a small atom of sodium. If we were to break apart this salt molecule, we would have sodium and chlorine atoms, but we would not have a salt molecule. It is possible to separate a molecule of water. For example, by passing an electric current through this blue-colored water, the water molecules are separated into oxygen and hydrogen gas, as seen here by these rising bubbles. In order to work more easily with elements, scientists have developed a system of letters and numbers, or chemical symbols, used to represent elements. Chemical symbols use one or two letters from the name of the element. For example, the element sulfur, shown here, is symbolized by the letter S. Sometimes two letters are used. Such is the case with copper, symbolized by the two letters capital C and small u. Sometimes the chemical symbols are derived from the Latin word for the element, as is the case with lead, which has the chemical symbol Pb from the word plutonium. As we discussed earlier, elements can be represented by chemical symbols. Chemical symbols can be placed together to make a chemical language. Different chemical symbols can be placed together to make a chemical formula which can represent a compound, such as copper sulfate. A chemical formula is an abbreviated way of symbolizing chemical substances. For example, you may already be familiar with the chemical formula for water, H2O. The H stands for hydrogen, and the O stands for oxygen. What does the 2 stand for? 2 means that there are 2 atoms of hydrogen. The small 2 is called a subscript. A subscript is a small number written below a letter or number. It indicates the number of atoms in the compound. Here you can see sulfuric acid reacting with a piece of metal. Sulfuric acid is important in making fertilizers, fabrics, and plastics. The chemical formula for sulfuric acid is H2SO4. It is made of 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen. In summary, we have explored how all matter is made of elements, and how each element has a definite atomic structure. In many cases, elements combine to form compounds that can be represented with chemical symbols and chemical formulas. So the next time you see some interesting matter, think about the elements and compounds which make it up. You might just look at your world a little differently. Fill in the correct word when you hear this tone. Good luck, and let's get started. Number 1. A pure substance is the throughout. Number 2. An is a simple pure substance that cannot be changed into a simpler substance. Number 3. An is the smallest piece of matter that cannot be commonly broken down. Number 4. Are the negatively charged particles in the atom. Number 5. The is the center of an atom. Number 6. The electron is the region where electrons would probably be found. Number 7. A is a pure substance made of more than one element. Number 8. A is two or more atoms that have bonded together. Number 9. Chemical are used to represent elements. Number 10. Chemical are used to represent chemical substances such as compounds.